Hello everyone, my name is Wei Li. Today I'm so glad to present our research here instead of my research teams. The title of our research is Machine Learning Driven Container Scheduling for Edge Empowered Microservices. My presentation contains these six parts: introduction, research review, research design, evaluation, result and discussion, and conclusion. So I'll start from introduction. Now, microservices architecture is designed for large, complex software applications that consist of one or more microservices, each of which can be deployed independently. The design principle of microservices architecture is a service-oriented, self-managed, and lightweight framework, where each microservices completes only one task, and the number and the scale of services are determined by business function. Now, Docker container technology has greatly reduced the complexity of system deployment, enabling faster service rollout and improved system resource utilization. But the challenges here is that traditional virtual machine scheduling algorithms are not optimized for containerized environment, especially in edge computing scenarios. So the aim of our research is to employ machine learning algorithms to optimize container scheduling strategies for microservice application in edge computing environments. Especially the k nearest neighbors KNN and Bayesian personalized ranking BPR algorithms are utilized to dynamically adjust container scheduling strategies. The traditional architecture of large systems and websites was typically centrally developed, often using a bottom-up multiple-level design. In 2012, microservices architecture was first proposed. The distinctive feature of microservices is that they are completely component-based and object-oriented. Uh, according to the literature review of 85 documents, we found out that for different types of services, there are different uh, architecture models. Here we'll list the four commonly used types, which are multi-service instance per host, second, a single service instance per host, single service instance per container, and serverless. Within our research, we propose another architecture model, which is named machine learning-based container deployment. We found that containers can be accurately and quickly adjusted in real time based on the current load pressure of the service using machine learning algorithm. In the design of the experimental setup, we adopted a pre-test and post-test design. Both groups are measured before the experiment is conducted. The implementation and the testing process consists of two main phases. The first phase is an accounting application based on microservices architecture, and the second phase is a recommendation system based on machine learning. This picture shows the details of our architecture. As can be seen that in total there are four layers within this architecture, which are presentation layer, communication layer, service layer, and the data layer. The presentation layer is responsible for data and page display. The communication layer identifies data interactions methods within the system. The service layer is the core of the system, in which we utilize the three different types of services, which are statistic service, account service, and notification service. The data layer is meant to store the data. We utilize a recommendation system engine tool, GORS, So this picture shows the details of GORS. It implements 7 scoring models and 4 ranking models, and supporting data loading, data segmentation, model training, model evaluation, and parameter search. In our research, we compared two commonly used machine learning algorithms, KNN and BPR. To compare the performance of those two methods, we use a cross-validation to build up models and verify model parameters. So how to evaluate these two algorithms? In our test, in total, there are 3 phases. First, microservices benchmarking. This initial phase is dedicated to obtaining the maximum throughputs and processing time for each individual microservices. And the second phase is to use KNN machine learning algorithm to adjust the deployment strategies for each services in the microservice application. The number of the container of each services is adjusted according to the deployment strategy given by the KNN algorithm, so that this request can be processed faster and avoid the accumulation of requests. And last phase is to verify the prediction accuracy of KNN and BPR algorithms. In our research, we utilized the movie lens 110 dataset to train the 2 models and to verify their accuracies. So here is the result of our test. As I just introduced that, the first phase applies a graduate increase in throughput, that is the number of requests processed per second, to obtain and record the average processing time, APV. These 3 pictures showed the time consuming with different levels of a request of different services, which are account service, statistic service, and the notification service. And those 3 levels of request are 1 request per second, 10 times request per second, and 100 times per second. It is easy to notice that notification services is increasingly affected by throughputs. And these 3 tables showed the time difference with and without machine learning algorithms. Similarly to text 1, we compare all the 3 types of services: account, statistic, and notification. So the first column of the table is the different types of throughputs: once per second, 10 times, and 100 times per second. The second column is the APV without machine learning. And the third column shows the APV processing time with KNN machine learning algorithm. And the last column shows the improvement rate when using machine learning algorithms. We notice that with the increase of throughputs, the impact of machine learning on processing time became significant. The third test shows the competitive results of 2 machine learning models, KNN and BPR. Here we list the 2 groups of results, account and statistic services. We can see that both KNN and BPR have good performance with lower throughputs, such as 1 request per second. But BPR method has better results when throughputs increase. For example, when the output is 100 requests per second, BPR method has 11.1% increase compared to KNN. So this result shows that BPR method has a better performance than KNN algorithm. So as a conclusion, our study explored the use of machine learning to adaptively modify continuous deployment approaches for microservices application in edge computing setting. We found out that machine learning algorithm can help with obvious uh, faster processing or shorter processing time. Also, we discovered that BPR is even better than KNN machine learning algorithm. However, within our research, we overlooked how frequent changes could affect business operation, and our research lacked exploration into scheduling and their request volumes. So this could be our future work. Okay, thank you.